Okay, let's look at this problem. Remember, I sent out an email saying there's a typo. The equation should be ut is equal to uxx plus 1. And we want to find an equilibrium temperature distribution if one exists, and then for which values of beta does one exist. Okay, so remember, equilibrium temperature distribution means ut is equal to 0. And so the equation becomes uxx is equal to minus 1. Then ux, if I do one integration, is equal to minus x plus c1. And then u would be minus x squared, over 2 plus c1x plus c2. Okay, so let's think about what the boundary conditions tell us. So I know that the derivative at 0 is going to be equal to 1. So in other words, if I plug in 0, I'm going to get 1. So this tells me right away that C1 is equal to 1. Okay, similarly at L, if I plug in L to the derivative, I should get beta. So beta is going to be equal to minus L plus C1, but I know C1 is equal to 1, and so this is only going to work out if beta is equal to 1 minus L. Okay, so we know there's only going to be an equilibrium temperature distribution if beta is equal to 1 minus L. If beta is not equal to 1 minus L, the fact that there's a source of thermal energy means there's not going to be an equilibrium temperature distribution. And we'll talk about more. We'll do the explain physically part after we get a little more information. Okay, so then we know that u of x is going to be equal to minus x squared over 2 plus x plus c2. And so now we want to determine what C2 is. And we have to figure out what piece of information we have. Well, there's a couple of things we want to note here. One, you know the initial temperature distribution, and we haven't used that yet. And so the question is, can we use the initial temperature distribution to determine what C2 is? And if you remember in class, the answer for this type of problem is yes, we can do that. And it goes like this. So what we want to do is show that the total temperature or the total energy in the rod is constant. Okay, and we're going to do this in the following way. We're going to use the work that we did before in problem 2 here. This is the total energy in a homogeneous rod. Okay, and so we're going to have C rho A u of xt dx. This integral is the total amount of energy in the rod at time t. And we want to show that the derivative is equal to 0. Because if the derivative of the total energy in the rod is equal to 0, it means the total energy is constant. Okay, and so I'm going to write this as C rho A times the integral x equals 0 to L. Now this is an x integral and a t derivative, and so I'm going to put the derivative inside the integral here, and this is going to be the derivative of u with respect to t, xt dx. This is C rho A. Okay, but now we're going to use the fact that we're assuming that u is a solution to the PDE, which means ut is equal to uxx plus 1. So this is uxx plus 1 dx. This is C rho A times the integral, I'm not going to write the integral anymore. Okay, by the fundamental theorem of calculus, the integral of uxx from x equals 0 to x equals L is ux of L, ux of L minus ux of 0, and then the derivative, the integral of 1 from x equals 0 to x equals L is just going to be L. Okay, now we know ux of L, okay, u satisfies the boundary condition, so ux evaluated at L for any t is equal to beta. Beta is 1 minus L, so this is 1 minus L. Minus, well, ux of 0. What is ux of 0? Well, again, it satisfies this boundary condition, so that's 1, and then plus L, and this is equal to 0. So we have shown that the total thermal energy in the rod is constant. Okay, so how can we use that? Well, this is the temperature distribution. So the integral of u at x is going to equal the integral of u of x0. So what I'm saying is if the total energy remains the same, then the total energy at the beginning is the integral x equals 0 to L u of x0. This is going to be equal to the total energy in the rod at any other time, x equals 0 to L u of x t. In particular, it's going to be true when u of xt is equal to this equilibrium temperature distribution. And if I divide both sides by rho, or by c rho a, I get that the integral from x equals 0 to L f of x, because that is u of x0, is equal to the integral x equals 0 to L. And now I'm going to plug in my expression for u of x. So this is going to be minus x squared over 2 plus x plus c2 dx. Okay, when I do this integral, what am I going to get? What will I get on the right hand side? So this is going to be minus L cubed over 6 plus L squared over 2 plus C2L. And if I solve for C2, I'm going to get that C2 is equal to L squared over 6 plus L over 2 plus 1 over L times the integral x equals 0 to L f of x dx. And then the equilibrium temperature distribution is going to be u of x is equal to minus x squared over 2 plus x plus c2, which is L squared over 6. Actually, this is a minus sign there. Plus L squared over 6 minus L over 2 plus 1 over L times the integral x equals 0 L f of x dx. Okay, so now I want to do this explain physically part. What's happening here? So notice. So I'm writing extra big because of the way this is. So on your homework, you should be able to write this all on 2 pages. Anyways, so when I explain physically, let's think about what this means. So remember that Q of x, in this case, Q of x is equal to 1. Q of x is the amount of thermal energy created per unit volume per second. So the amount of energy being created from in the rod is going to be equal to the integral of Q of x times the surface area of the rod dx. And since x is equal to 1, this is just going to be L times A. Okay, that is the amount of energy being created within the rod. Okay, now let's look at the boundary conditions. What's going on with the boundary conditions? Ux of 0 is equal to 1. If Ux of 0 is equal to 1, this means phi x of 0 is equal to minus 1. Okay, and remember, sorry, not phi x of 0, just phi of 0 is equal to minus 1. And remember, phi is the energy flowing to the right per unit surface area per second. So if I multiply both sides of this equation by A, what this tells me is that I have minus A units of thermal energy flowing out of the rod at the 0 endpoint per second. And similarly, if I look at the boundary condition at A, I have A times phi of L is going to be equal to A. Well, phi of L is just equal to minus Ux. Ux is equal to beta. Beta is 1 minus L. So this is L minus 1. Okay, now if you consider the case, let's just consider the case first where L is bigger than 1. Then what this means is what this means at the left endpoint, we have minus A units of energy flowing out. Because remember, phi is the flow to the right. So at 0, it's minus A energies. I have minus A units of energy flowing per second. That means I have A units of energy flowing out of the rod at the left endpoint. On the other hand, if L is bigger than 1, A times L minus 1, that's going to be positive, and so this is going to be the total energy flowing out of the rod at the right endpoint. It's positive there, so it's going to be flowing out. Okay, so what is the total amount of energy I have flowing out per second? It's going to be minus A plus AL minus A. Okay, so the total energy flowing out of the rod per second is A times L. On the other hand, the total energy being generated in the rod per second is L times A. And so in other words, the total energy flowing out is the same as the total energy being created in the rod, and so the energy distribution is constant. Okay, and I'll let you think about what happens if L is less than 1. On the right endpoint, we'd have energy flowing into the rod, and you can do a similar calculation to show that we have a constant thermal property. Okay, so that reasoning, or this reasoning with the integral, or not constant thermal property, we do have that, I mean constant thermal content, or this reasoning with the integral are sort of related to each other.